Hello, today we have integer, some integer value n up to the 10 to the power of 5, and we want to have a concatenation of values n up to n. So in a binary representation it is 1, then 2, then 3, then 4, 5, and so on. And the number can be big, so we have to do this modulo 9 zeros plus 7. So the solution is just brute force, and it is accepted. Brute force. And to brute force you have to convert to string, shift to the left, and by the length, and then add this operation of the current x, and then do this model. And this solution is accepted. It is quite slow. Let's look at the code. So here is the code, and it is 600 milliseconds. This is because of to-string conversion, and I use this like shifting by individual bits, but you can also do shift by entire number. This is the first optimization, and let's look at the final step of this optimization. So here is it, and this is a fault. This is x to string, but you can have countLeadingZeroBits, and this would be faster a little bit, like 127 milliseconds. So the solution also has logarithmic time, the logarithmic time solution. So let's look at the code, and I will try to explain it. So the code is quite scary. Let's open non-minified version. Okay, it's in Kotlin. So the basic idea is that we can recognize these kind of operations we are doing many times. So if we have a result, and to get a new result we are doing the previous result, then we multiply it by 2 to the power of L. This is a shift operation, and then doing plus x, and then for the x new we are doing exponentiation plus 1. So this is kind of operations that we are doing n steps, and the linear algebra can help us. What is it? It is conversion this into matrix multiplications. And to find this matrix multiplication, so like R new x new equal some matrix times R x previous. So this is how it works, and then if we do n times, we just making the matrix power of n, and this would give us the solution, and the final r would be multiplication. So now let's think about how we can build this matrix M. Again, the x is x plus 1, x new. That means maybe I should just use this one. And that means we have to second type, introduce a second type, so it goes here to the 1, the third row, because this is a different type. It doesn't have x in it. Now the representation of matrix is for 3 columns. We have to do like this: RX1, and this would be 3 values. 3 goes here, R, then 3 goes here, X, and then 3 goes here. So for the R equal R times 2 to the power of L plus X, we should make this R times R, it is 2 to the power of L, then the X goes here, is 1, and 0 once. Now the X value is 0R, 1X, and 1, 1. And for the 1, it is just 0, 0, 1. So this is a matrix that we should exponentiate. Now the trick is that we have to do this kind of modulo operation, and the exponentiation with the modulo operation is a separate task, where you have to do the binary exponentiation, just 2 to the sum m to the power of n equal m to the 2n divided by n plus m is like this. So and this is divided by 2, I think. And this is a m times m. So let's look at the code. For the power, we have, if the bit is set, we're doing multiplication by base, and for other case we're doing squaring operation, and then we divide it by 2. And matrix multiplication is just three for loops. And the first value is 1. So this is identity matrix, like power. And this is a matrix of M with the first value of 2 to the power of L. So this is it. And the final value is multiplication row by column. And in the Kotlin, this solution is not very fast. It's the same time, but in Rust, it's actually faster. It's 2 milliseconds compared to 23 milliseconds of a fault operation. So the Rust is much cleaner. I also use this 1D arrays instead of 3x3 matrix because it is faster and it is less code. And then another interesting part is this from function. It was a surprise to me that you can write it like this. The I is just derived from the result signature. So that's it for today.